hear the term pure, what do you think? What does that mean to you when something is pure? It turns out there are a couple different meanings that we can have. You can talk about pure orange juice. That means you have juice that comes from only the orange tree. But relative to a chemist, orange juice is anything but pure. Relative to a chemist, pure means the material consists of only one material. If, for example, you have pure water, you've got only water molecules in there, right? So when we look at orange juice, it's got water, it's got sugars, it's got pulp, it's got a whole array of different materials. And it's anything but what a chemist would call pure. Let's look at some definitions of what we mean by pure, all right? When we talk about pure, let's see, we mean, relative to a chemist, we mean consisting of only a single element or a single compound. If you had pure gold, that means you have nothing but gold atoms, and we would say that it is pure. If you had pure water, you've only got water molecules. This brings up an important point. If you had water, you know how small water molecules are? In a sample of water that you can hold or look at, you've got billions upon billions upon billions of water molecules in there. And what if one, say, arsenic atom snuck its way in there? You know what? It's no longer pure. Because if pure means you've only got one thing, just one arsenic atom amongst billions and billions and billions of water molecules, and you ruin it. You see, when we talk about something being pure, we're really talking about an ideal state, because molecules are so small, you can never really get to a sample that's 100% pure. It's an ideal state. But that doesn't hold us back from thinking about the idea of there being a pure sample. It might be 99.999% pure, but that's sometimes good enough in terms of when we want to classify materials. Impure. You know, that's simple. That means it's not pure. That means you've got a mixture. We know about mixtures, and most everything around us is made of a mixture containing two or more elements or compounds. Now, this is reality. We look around us, everything is a mixture of elements or compounds, right? We might try to purify a mixture, and that's an important process and something you learn how to do in chemistry. And you purify mixtures by separating the components as best you can, right? So that's what we mean by pure and impure. And when chemists try to classify matter, they classify it based upon these two concepts, whether it be pure or impure. Recognize pure as an ideal state, impure is more of the real state. Pure, let's take a closer look on this side of this chart. If your material is pure, it is either an element or a compound. Say it's pure gold, you've got nothing but gold atoms. It's pure sulfur, you get nothing but sulfur atoms. That's straightforward. How about over here? Compound. If you have pure salt, you've got nothing but sodium chloride. Wait a second. Sodium, chloride, that's two things. Sodium and chlorine. What do you mean that's pure? You've got two things in there. You've only got one thing in there. That one thing is sodium chloride. Sodium chloride isn't sodium and it isn't chlorine. It's uniquely sodium chloride. So when we say we've got sodium chloride, that's one material. And if you got nothing but sodium chloride there, sodium and chlorine in a 1-to-1 ratio, you've got pure salt. Carbon dioxide, you've got nothing but CO2 molecules. You've got pure carbon dioxide or ammonia, what have you. As long as you have one compound, then you'd have a pure material. So it's either an element or a compound when you talk about something that's pure. On the other side, we talk about impure. You're necessarily talking about mixtures. If it's a mixture, you've got two kinds of mixtures. You can have a heterogeneous mixture or a homogeneous mixture. Let's look over here at the heterogeneous mixtures. Examples would be like sand and water. Take the sand and pour it in the water, stir it up a little bit, and you'll see you've got a liquid and a solid together. And the key for understanding what we mean by a heterogeneous mixture is that you're able to visually see the different components. You might need a magnifying glass or a microscope, but you can look and see there's one component and there's the other, and distinguish between the two. Hetero means different, so you've got different components in there. And so you have oil and water. Shake it up, you can see the globules of oil in the water. You can see the two different phases there. Or sand and salt, sand being a solid, salt being a solid. Put them together and stir it up, and you'll be able to see, oh, there's a grain of sand, there's a grain of salt. That's an example of a heterogeneous mixture, whereby you can actually see the different components. Over here on the other side, when we talk about a homogeneous mixture, it's mixed so finely that the molecules are mixed together, down to the submicroscopic level. And that's nothing we can see visually with our eyes. If it's mixed so finely down to the atoms and molecules, and we can't distinguish visually the different components, we say it's homogeneous, meaning it's consistent throughout. You should be able to look at one part of the mixture, and it will look the same as any other part of the mixture. Homogeneous. But wait, if it's a homogeneous mixture, you've got two choices. It branches out. It can be either a solution or a suspension. A solution is an example of a homogeneous mixture whereby the components are all in the same phase. The phase can be a gas, solid, or a liquid. Here, when we talk about air, air is a mixture of the two gases, nitrogen and oxygen, and it's homogeneous, right? And they're both of the same phase, so that makes it a solution. Salt water, you take the salt, you dissolve it in the water, that becomes a solution. It's in the same phase, you see. White gold, that's an example of a solution, a solid solution, where the platinum or palladium sometimes is used, and gold are mixed together. And so you have gold and palladium or platinum atoms mixed down at the submicroscopic level, so you can't distinguish them from the macroscopic level. You've got yourself an example of a solution, and solutions can be solid too. The other side is the suspension. In a suspension, what we've got is a homogeneous mixture that consists of components that are of a different phase. In the solution, the components are all in the same phase. In the suspension, the components are in a different phase. Milk is a good example. Milk is, it has water in it, which is the liquid, but it has proteins that are floating around in the water. And that makes it an example of a suspension because the proteins are really solids suspended in the water. Fog is a good example. With fog, what you've got are tiny little water droplets that are in the liquid phase, but they're so tiny that they're suspended in the air, right? And that makes it a suspension. And because you've got so many tiny water droplets, you can't see through the fog. That's why the fog is opaque. And when the fog goes up into the sky, we call it a cloud. Got that? Those are examples of suspensions, as is blood. Blood is an example of a suspension of these solid proteins in water, suspended in water. What we can do is take a suspension and separate it into its components based upon the differing densities, which is a physical property. Because think of this, in the suspension you've got a solid and a liquid together. If you were to spin it really fast, like in a centrifuge, the solids would be thrown outwards and you'd be able to separate. That's what they do with blood, actually. They'll take the blood and they'll spin it in the centrifuge, and the solid proteins are thrown to the outside, and you'll separate the components. The red blood cells will be at the bottom, the white blood cells in the middle. You can see you got more red blood cells than white blood cells, and you could probably guess which is more dense, the red blood cells or the white blood cells. And up above, you've got the blood plasma, which is the solution that contains these solid materials, the white and red blood cells. And that's it. What do you think? If you got all this, you'll be able to answer the following. Impure water can be purified by removing the impure water molecules. Removing the impure water molecules? What's an impure water molecule? Well, let's see. Water molecule is H2O. Why don't we do H2O2? Maybe that's impure. H2O2 is not water. Water is H2O. You know, you either have a water molecule or you don't have a water molecule. How about removing everything that's not water? If you want to purify something, how about C, breaking down the water to its simplest components? Breaking down the water? If you break down the water, you no longer have water. What? You want to take the water and break it into hydrogen and oxygen? You haven't purified your water. You've destroyed your water. Think critically about this now. One more choice, D, adding some disinfectant such as chlorine. Add. You want to purify something by adding something? So the tap water is coming through into your kitchen and you want it purified, so you add chlorine? Maybe you add the chlorine for another reason, not to purify the water, but to do something else. So you got that? You know this is a concept check in your textbook, which you're going over thoroughly, aren't you? D? A, B, C? Which one was it? By now you should know the answer. By now, you should be able to explain your answer to someone else.